Hi, this time what we have in mind is talking about, comprehending the basic ideas on configuring port pins. You see, the idea of being able to organize a pin as an input to the system or the same pin this time as an output from the system, the microprocessor. So this is what we have in mind in this video. So it is attaining the unit that you will find in digsys about this theory on port configuration. It is about the port register and the trace register that goes together in a way that you can define the way the port works. So to talk about input-output, okay, the basic input-output, we have to be in P9 because here is where we introduce the basic concepts on microcontrollers, right? So in the learning materials of this project, okay, because this project is devoted to the invention of a one-digit BCD adder, just a simple example to put into motion these basic ideas on microcontrollers. So if this is what we have in mind, learning about basic I/O, we have here the link down there in the learning materials and tutorials. Here you have this stuff that has been placed in a different unit. Let's talk about the basic concepts on port pins, data bus, three-state gates, and direction configuration. So if you click this link, you jump to this unit, on how it is possible to make, in some way, a wire bidirectional. This is the purpose of what we have in mind. How is that possible? To consider a pin, and this is a chip, you see, you have a chip, and this is a pin. How can it be declared as output and another time later on, perhaps in the same program, as input? How can you do that instead of using the typical thing that is fixed direction, a single direction output and a single direction input? So two different pins. How is that possible to use a single pin for both directions, depending on the program? So if this is what you like to invent, we have to talk first of all about the new gate that is here. And it's new because we have, well, and in this introductory course, because I have not yet talked about it, okay? The three-state gate. What is this idea about? So, well, it is a gate as usual. For example, it is a buffer, okay? So you have the buffer connected to the power supply and the ground reference, and this buffer has an input that we usually name X and an output that we usually name Y. So, well, this gate, you see, is special. Apart from the typical input and output and power supply and ground, you have this extra input, the control pin. It is a controlled gate that has this special property of generating a third state that is not a 1 or a 0. So the idea is that at the input you have as usual a 0 or a 1, that it maybe came from a previous gate or just a pulse generator, whatever you have to generate logic levels, okay? So you have the typical logic level at the input of this three-state gate. And then there is the output. And the output in some way, as usual, is connected. It cannot be simply a wire on the air. It is connected to, the Thevenin equivalent of another gate or just a lead circuit, whatever you have in mind. That here is represented by a load resistor that usually has a large value in the range of mega ohms. So the next circuit is not charging this gate, all right? So what we are going to find here is that idea that for a given value of the control pin, what you will get is a third state, a third state that it is called three-state. So in this kind of gate, it is possible to get, as usual, a 0, you see, the typical 0. you can get the typical one as if it were a normal buffer, but then it is also possible to have this third state. It is like having this output wire exactly in the air, not connected to anything. That way, so it is in some way fixed to a voltage that is not known. It's unpredictable. No one knows what kind of voltage is in this wire if it is kept in this third state. And how it is possible to imagine such gate? Well, because we have this idea here. Look at this. If the control pin happens to be 0, okay, if this is what you've got in your control pin, okay, 0, the gate becomes a normal gate. The model of this three-state gate is nothing but a normal buffer, but that is disconnected just simply by a switch. Okay, is disconnected. The switch is off. And so here you are. You see, the wire that is here represented in red is in this new state. It's just a wire, you may call that way, a wire in the air, not connected to anywhere. Well, here we have represented that connection using high value load, but it is very possible that here you have, I don't know, 10 mega ohms. So this is really a wire completely isolated to the rest of components in the circuit. So this is what we call three-state, and that idea is going to give us opportunity to invent many more circuits now. And when the control pin happens to be 1, well, what you've got is a typical buffer, because now this output switch is closed, is kept closed, and so it's on, and if X happens to be 0, you get a 0 at the output. If X is happens to be 1, you get a 1 as usual, right? So look at this, you have a typical buffer as usual, or you have a typical buffer but with the output disconnected. This way, as a switch. Well, if you look later on the technology about these switches and the kind of gates that you can invent here, you will use CMOS technology, for example, combining PMOS, P-channel MOS transistor, and N-channel MOS transistors. You can invent this ideal switch, almost ideal switch that is placed in the output of a gate, and making this wire that way in the air, exactly like this, okay? So you may very well say that, you see, the gate is disconnected. The gate may be driven, you see, by the voltage generator. You see, you may drive, if you like, the gate as usual, but the gate is completely isolated, has no connection to the output. And that is the fundamental idea of the three-state gate, okay? So if you can go and disconnect outputs, you can very well organize this bidirectional pin. It may be configurable as input or output, the same wire, okay? Because you can place one of these special gates here between, for example, the internal circuitry of the microcontroller or any other digital device and the pin. You can configure here with precisely three-state gates and this control extra pin. You can configure that idea, okay? So, and this is a kind of a circuit to do that. You can connect like this, you see? The input, the output, and then the three-state that is driven by an inverter, and the same control now is driving the other gate that is connected like this in the opposite direction. So both gates has the same control signal, but you know it is affecting differently. So because of this knot, the gates can never be running together at the same time. If control happens to be 1, this one will be on, and because you have a 1, you get a 0 here, and this one is going to be off, and the opposite the same, you see, 1 on off or off on. So as you can imagine, it is easy to to think that you can program this direction or you can program the other one. Exactly, this is what is represented in the next picture, right? Look at this. That simple thing, okay? With control equal 1, what you've got is this input direction, because the gate that is enabled is that one here that connects the pin in this direction and towards the microprocessor internal circuitry, keeping this other gate off. And just the opposite happens when the control pin is 0. Now the gate that is kept off is that one, so the direction is clearly an output. So you can do that for any pin in any digital chip. So this is something that can be very well materialized and solved technologically in every chip that you like to control. With this idea, okay, if you have a pin or a series of pins that may be bidirectional, you see, that enhances the applicability of the chips. If you have a reduced number of chips, of chip pins, you can use them in different applications, sometimes as inputs and sometimes as outputs, and that means flexibility and versatility, and that is something interesting for every chip, because the number of pins is something that is not well, you have just a number of pins, and if you have this opportunity, that's a lot better, okay? The chip that you have in mind can be adjusted and tuned for more applications. So this is the idea here, okay? And apart from that, related to the pins, there are another feature that must be considered. If you imagine the typical architecture of a microprocessor, okay, you may very well think about this idea of bidirectionality. Yes, you have a data bus. So the concept of a bus is just like that. The idea that you have a wire that is connecting all the chip subsystems, the CPU, the RAM, the I/O ports, and many more modules that you've got here. So these kind of copper wires connections are connecting everything. And sometimes, you see, by means of another bus, the control bus, you can decide, for example, if the CPU is outputting data to an internal memory position, to write this data in a memory position, and later on perhaps you like to input, you see, a port register, a port pin through the same wires, you see, just now in opposite direction, you see, to the CPU working register. Something like this is very possible if you think that internally in this structure of a microcontroller you have this idea of a bus. All right, a bus for the data, normally in this kind of microprocessors that we are using here, 8-bit data bus, and then you have an address bus, and then for example, to pinpoint every single memory position in the RAM, and then the control bus. That is for this kind of, you see, sequencing of operations and being able to switch directions of those wires here if necessary, right? So that is the very idea of connecting blocks internally in a microcontroller. So look at this. Here, now you have this two-state gate connection repeated 8 times or n times. You see, the same architecture copied for every single wire, so that you can choose the directions of these bus wires, whatever you like, by means of a control pin, right? So sometimes the control system of the microprocessor, as we have explained now, may decide to go in this way, and sometimes it will choose to go in the other way. So, right. So what is left now perhaps is to go back to the idea of the port. because precisely is the port pin what is configurable. You have a port pin, for example, the port A bit 0, that is configurable. It can be at the same time input or output. So what these people has decided to do, you see, and what you see in this picture, is that if you are saving a 1 in the trees in the data direction register that is kept in the shadow, you see, this trees register is mapping every bit of the port. So if you are saving a 1 in this register, you get that the port pin associated to this trees bit becomes an input, like that. So now this port pin is for reading, but perhaps the other one, the bit number 3 in this example, can be programmed to be an output. So you see, because what you've been saving in the trees is a 0. That is the way it works in microchip chips. That simple way, all right? So if this is the concept, you see, saving direction pins, direction bits, you see, for every single pin on the port, you can analyze now, to finish this brief introduction to the port idea, you can analyze why not the very idea or the very circuit that is given to you by microchip. Okay, look at this. This is the generic I/O port. You have a data latch, a trees latch, you have control signals like this one, write the trees bit, you see. You have the pin symbol, they represent the pin like this. Okay, so you have a tree state. You see, you have many tree state gates to fulfill this functionality of being able to send bits as an output, or if this gate is blocked, you see, you can capture the bit information and make it go through this input buffer to where? Well, to another latch, as you can imagine, or another flip-flop. So this is the circuit, and this is the concept that you've got here, the possibility to save what you are reading and the possibility to write what you are writing. You see, you are writing here, okay, and you are reading, okay. So let's do that again. You see, you can write to this pin, right? You see, so it is the value that is kept in this queue, it's an output, or you can read. That latch is going to translate the data input to this other queue, you see, to this other wire, and then get was. Well, what you are going to write or what you are going to read in the end is going to go to the same shared and bidirectional data bus that we have just explained something about it. Okay, so look at that. You have the data bus for this multiple purpose, the same data bus wire to write through this latch and save in this 1-bit memory cell what you like to write. Okay, to write the content of the trees latch, so this output is keeping here the control bit to manage this gate, okay, and the same data bus is for reading what is saved in this queue because you like it. If you program that, you see, if you program that by means of this other tree state gate, okay, if you like to read RD, you see, you like to read the port content, so you can very well give that level 1 here. This level is going to enable this tree state gate, and what is saved here in this flip-flop will go to the data bus in this direction towards inside the chip. So very well. Well, you can keep that circuit. It is all right. It is perfectly well understandable. What we do here in CSD, you know that. What we do, you see, almost or many times is to go to data sheets and where we go to data sheets and yes, analyze this kind of circuits at this level, but then if possible we have something in mind that is just what you see here in this picture. All right, what if I ask you now to design such port as another exercise? So look at this. This is the way to finish this explanation. What if now I ask you to design, and not the same, because this is in some way proprietary from Microchip and you know just some details of this. So what I'm asking you, for example, is what is if you design an adaptation, okay, of this circuit using something from previous projects. For example, what if you design a hardware adaptation of the circuit using P7 and P8 concepts and circuits, you see? Because what is this? A latch. Yes, this is from P5. And but there is a clock here in some way, so it's a flip-flop, data flip-flop. Okay, and what is this idea of controlling the port direction and the like? So perhaps it's an advanced system, you know, a control unit and the data path being that simple as some 1-bit memory cells. Okay, so what if you go and design a hardware adaptation of this circuit using previous concepts so you get it in VHDL? Is that possible? Probably yes, because this is what I'm proposing you in the last picture 5. So now if you browse the web page and you go down here, you see what I mean, you see? All right, let's in some way use our typical circuits from previous projects to replicate and adapt. Not the same, but the same. I mean, adapting means getting something that is giving you the same functionality. So this is it, okay? This is it. You have a chip 1, chip 2, chip 3, all of them the same kind. Data register 1 bit, something that you learn to do in P7. All right, you see, you have the load and the data, so the data can be captured, you see, whatever it is, because you have this function table. If data is 0, it is copied 0. If data is 1, is copied 1 to the queue, plus, but plus, you know, to do that correctly after the rising edge of the clock. So this is why you can imagine this as a typical circuit that works with a clock. So you have 3 clocked data registers 1 bit, 2, you know, to save the data in this direction or to save the data in that direction. And you can even save, you see, well, in that direction, you see the chip 2 and the chip 3. What is the chip 3 doing? You see the chip 3 is saving the trees. Let me erase the many lines that you've got here. You see, this is the trees bit, okay? This is the trees bit that you've got in the port configuration. So look at this. If you are saving here a 0, this gate is going to be on, and so this register is going to supply data to the port. But if you are saving a 1, you see, if you are saving a 1 now here, this gate is going to be blocked. So this value, okay, is going to be kept here, and it's not going to reach the port pin. On the other hand, the port pin can be read by means of this buffer, and the data is copied to the queue. So here you are the value that is read from the port pin when input. That way, and it is input when you have a 1 in the trees B. So you see, this flip-flop, the one that we call chip 3, is nothing but what you have seen above, you see, like here, like in this tree. So this is in some way the section of the trees bit and the port bit, you see, the port and the trees bit below, right that, okay? So then finally, if this is the circuit, composed of some flip-flops, as you see, flip-flops, and logically some three-state gates. And the way to implement the three-state gates are explained in a P8 and in a RAM example. In the RAM example, you see how to implement a three-state buffer in VHDL. That is where you can find how to implement three-state buffers. Well, in VHDL, you see. So that's it. So you see, in the end, you can discuss very well how by means of several control lines, you know, a microprocessor or control unit signals to control the read and the write to a given port and its trace bits. So not bad, right? Well, we are not going to work at this level, naturally. We only have in hand now here, you know, is to give some insight in this theory, okay? Because what we are going to do simply for the many applications that we have ahead now is to work about this simple idea, okay? Let's finish here. We will talk about the trees and the port, and we will imagine naturally that this kind of circuit is already solved from microchip, and we will simply use this port as it is, okay? Writing, you see, or reading, this is reading. We will read all the port pins in a single instruction, and we will assign the content of the port that has been read to a variable, a RAM variable, for example, type char. This is what we will do, a read operation. Or on the other hand, we will do just the opposite operation. Look at this. The value of the port register is just equal to the variable that is in the RAM. So you see from the data bus, the content of this RAM memory will go through the data bus to the port register and is going to be kept there, written. And by means of the control lines, this value that is kept in the 1-bit memory cell is going to be made available to the pin by means of controlling the three-state gates. That's it, okay?